Good evening and welcome to the Song of Urania. This is a podcast about the history of astronomy, with new episodes every full moon. My name is Joe Antonini. Astronomy has the distinction of being the oldest of the sciences. All civilizations had some knowledge of astronomy to one degree or another, and in many of these civilizations, knowledge of the heavens held an exalted place. Even societies that left behind no written records for us to study left evidence of their astronomy in their buildings and monuments. The first records that are definitively astronomical in nature are more than 3,000 years old. As you might imagine, astronomy has changed quite a bit in that time. The goal of this podcast is to trace the history of this subject through these 3 millennia. I want to explore how astronomers have thought, how they have worked, and how astronomy has changed over these last 3,000 years. A bit about myself. I'm an astronomer by academic training. I have a PhD in the field, but I am not a historian. However, I want to avoid what I see as a common trap that many astronomers fall into when talking about the history of their field. Most astronomers present a version of their history that could perhaps be called folk history, an analogy with folk etymology or folk medicine. What I mean by folk history is a version of history that a group of people tells themselves. Some folk histories, think of George Washington and the cherry tree, were invented out of whole cloth. Others, think of Paul Revere's Midnight Ride, or more relevant to our subject, the Galileo affair, have some bearing on reality, but have birthed myths that have begun to live in the popular imagination and for which the actual story is much more complicated. One of my hopes in this podcast is to separate out the folk history from the real history, to the extent that the real history can ever be discovered or worked into a single narrative. But I don't want to completely ignore the folk history either. While the stories of folk history are usually not literal accounts, they do convey real information about how a group of people sees themselves and what they value. As we trace the development of the science of astronomy, we're going to encounter people, ideas, and cultures which are really quite different from the people and ideas we're familiar with in our modern culture. Even the giants of science from just a few centuries ago thought in ways that we today would consider to be profoundly unscientific. But what I want to do is to really take their ideas seriously, on their own terms, not just the ones that happen to work out and are given a few sentences in a modern textbook, but also the ones that modern astronomers have forgotten. If we simply limit ourselves to those discoveries that meet the bar of our modern scientific criteria, we'll be ignoring almost all the work that some of the smartest people ever to have lived thought was important. We'll be failing to really understand how this knowledge was actually gained and how the science evolved over the centuries. There's an analogy I quite like due to Professor Lawrence Principe. Suppose that one day an American decides he wants to see more of the world and decides to go visit Japan. And after landing in Tokyo, he starts to wander around the city and take in its sights. Well, eventually he gets hungry, and after searching for food for a while, he stumbles across a McDonald's. And to his delight, he finds that this McDonald's serves Big Macs, and they taste just as good as the ones at home. Well, the next day he continues his trip, seeing the sights of the city, and again he gets hungry, and now he knows that there are McDonald's in Japan, so he goes off in search of another McDonald's. And it takes him a while, but eventually, with persistence, he finds another McDonald's and enjoys another Big Mac. And so it goes every day of his trip. He gets hungry, goes off in search of a McDonald's, and with some considerable effort eventually finds one. Well, finally, our tourist's trip comes to a close and he flies back home. And when he gets back, he concludes that the food in Japan is exactly like the food in America. There's just less of it. As we dive into the history of astronomy, we don't want to make the same mistake as our poor, benighted tourist. We don't want to assume that astronomers of the past thought the same way as modern scientists, approached problems exactly the same way as modern scientists, or even had a general worldview that could plausibly be called scientific. In short, we don't want to simply assume that astronomy in the past was exactly the same as modern astronomy, and that there was just less of it. Well, as we dive into the history of astronomy throughout this series, I really want to understand all of it. Not just the astronomy that has survived into the textbooks of today, but all the theories that didn't make it, even the ideas that we don't consider today to be scientific. I don't want to simply touch on the theory of epicycles as just a pit stop on the way to Copernicus's heliocentric theory, but to really understand the details and motivations of a scientific theory that survived for more than a millennium. And yes, we will even explore astrology in great depth as well. There's simply no way to understand the history of astronomy without understanding the history of astrology. The two are twin sisters joined from birth at the hip. Another facet that I want to look at over this series is the relationship between astronomers and the broader society. Today, many of us think of astronomy as an esoteric subject, untethered from the banalities of everyday life. This removed from normal life, I think, drives much of the allure of astronomy. It connects us to the transcendent in ways that few other things can. The only other subjects that really have the same grasp on us are perhaps music and religion, and for many of us moderns, not even those. It's perhaps no coincidence that astronomy has been associated with music and religion from the time of antiquity. Today, astronomy does not really serve a practical purpose, or at least to whatever extent it does produce practical results is entirely incidental. But it was not always so. The relationship between astronomy and the broader society has changed considerably over time. In some places and eras, astronomy operated as it did today, at some remove from the state, maybe depending on it for financial support or maybe not, in a sort of system of benign neglect. But in other eras and places, such as ancient China or ancient Babylonia, astronomy and the state were much more tightly coupled, and their interests sometimes aligned and sometimes collided. And in many, perhaps most societies, the study of astronomy was extremely practical. States depended on astronomy and astronomers to mark calendars, facilitate navigation, and perhaps most important of all, cast horoscopes. Kings, queens, nobles, they all depended on astronomy to decide when to go to battle, when to sue for peace, when to take medicine, and when to marry. So over the course of this series, we're going to dive deep into the way that astronomy was done throughout history. In order to prepare ourselves for this, I want to spend the rest of this episode giving a very broad sketch of the history of astronomy from antiquity to modernity to bring forward some of the themes and questions that will arise again and again over the course of this series. To help frame the overall evolution of this science, I think that it's helpful to divide the history of astronomy into three broad eras, which, to avoid any controversy, I will give very boring names. The first being what I'll call early astronomy, which lasted from antiquity to the 1600s or so, followed by the second period, which I'll call early modern astronomy, lasting from roughly the 1600s to the mid-1800s, and finally, modern astronomy, which begins in the mid-1800s and lasts to the present day. I break these eras up based on the problems that astronomy was attempting to solve and the methods that it used to solve them in these times. The astronomy of antiquity was founded in solving a problem that we don't really consider today to be astronomical at all, namely, how do we keep time? Ancient peoples noticed the regularity of the heavens and found that they were the most accurate way they had of setting their calendars. And there's no real surprise here. The heavens are extremely regular compared to terrestrial phenomena, and any agricultural society needs to track the course of the year in order to determine when to sow and when to reap. And as societies grew to be larger, more complex, more interconnected, keeping the society in sync with itself required greater precision in timekeeping. And the heavens, quite considerately, present to us three very obvious cycles to keep track of. The diurnal cycle, that is one day. Every day the sun rises in the east, comes to some peak in the sky, then sinks in the west, at which point it becomes night, and then the whole cycle repeats itself. Then there is, of course, the year. Over the annual cycle, the days get longer, the sun grows higher in the sky, the weather gets warmer, the plants grow, and then the cycle reverses. The days get shorter, the sun sinks in the sky, and the weather gets cooler, and the plants die. After 1 year, the cycle repeats itself. But how many days are there in a year? Well, we enlightened moderners would say that's easy. There are 365. Well, unless it's a leap year, in which case it's 366. But when are the leap years? Well, that's easy. That's every 4 years. Unless the year is divisible by 100, in which case there's no leap year. Except if the year is divisible by 400, in which case there is a leap year after all. Well, this is quite a convoluted scheme. And arriving at this convoluted scheme was one of the central problems of astronomy for millennia. The principal issue here is that there is not an even number of days in a year. It's not terribly difficult to determine how long a year is to within a day or so, but if you want your calendar to work over centuries or millennia, you need to know how long a year is to within much less than a day, to within minutes, even seconds. If your measurement is off, these inaccuracies will compound over time, the seasons will start to drift, and after long enough, winter will be in June, and summer will be in December, and everything will be a mess. And this is exactly what happened time and time again. Spring would arrive earlier and earlier in the year, kings would begin to panic, and astronomers had to come up with a solution by measuring the year more accurately. A further wrinkle that ancient astronomers wrestled with was the third cycle that is readily apparent in the night sky, the phases of the moon. Over the course of 1 month or so, the moon waxes from a barely visible crescent just after sunset to a full and very bright orb that is visible throughout the entire night, and then wanes into a crescent that is only briefly visible just before sunrise, before starting the cycle all over again. The lunar cycle is very convenient for human societies because the month is a nice intermediate duration between a day and a year. A day is so short and a year is so long, but a month is something you can work with. Consequently, many societies used the month as an additional way to keep time. But again, there's a problem. The length of the month does not neatly divide the length of the year, nor does the length of the day neatly divide the length of the month. And what's worse, the month is not exactly regular. Some months are slightly shorter, others slightly longer. As we are going to see over the course of the series, much of the earliest astronomy was concerned with this thorny problem of figuring out how long a month lasts. So astronomy had its roots in timekeeping, but this was not the only question that ancient astronomy was interested in. There were two other issues that occupied the astronomers of antiquity. The next issue was the motion of the planets. If you watch the heavens regularly, as you must if you're determining how long a month is, you'll notice that the stars generally maintain the same positions relative to each other. They form recognizable constellations. However, there are 5 conspicuous exceptions. There are these 5 mysterious stars which seem to move about the heavens over time. Sometimes they appear in one constellation, but over time they drift into another. But this drift is not regular, at least not obviously so. Determining where the planets would be over time was the second question that occupied the early astronomers. The final question arose later and was more philosophical in nature. What are the heavens made of? The ancients did not really have the means of answering this question in a way that we moderners would consider to be scientific or even really plausible, but that did not stop them from asking the question. And this question begat a further natural question. What's the relationship between the heavens and the earth? It's clear that there's some relationship here. The sun affects the weather and the planets. It was well known that the moon affected the tides in some way. So it was very plausible that the other planets would have other effects, subtler effects to be sure, but other effects on the terrestrial realm. Well, what was the extent of this relationship? Much of this is what we would today call astrology, but the ancient world did not recognize this distinction between astronomy and astrology that we today do. So these three questions occupied astronomers for millennia. Number one, how do you keep time? Number two, how do the planets move? And number three, what are the heavens made of and what's their relationship to the Earth? Now, a more standard history of astronomy will usually define the historical eras in relationship to the time periods of the broader culture. So you'll have one era as being the astronomy of antiquity, followed by medieval astronomy after the fall of Rome. And then it's standard to demarcate the boundary between medieval astronomy and early modern astronomy with the heliocentric theory of Nicholas Copernicus. But in my idiosyncratic division of the history of astronomy, where we have just three periods, the early modern, and modern, I view the work of Copernicus and Tycho Brahe and Johannes Kepler as more of a culmination of early astronomy than a radical break away from it. And this is not in any way to minimize the work of Copernicus. Of course, the work of Copernicus was of singular importance to the history of astronomy, but the reason I do this is that, at least in my idiosyncratic division of the eras, they're distinguished by the problems that astronomers were solving and the methods that they used to solve those problems. And the problems Copernicus was solving were the same as the problems that Ptolemy was solving. Copernicus proposed a different solution, a very different solution to be sure, but a different solution to the same problem of modeling the motions of the planets. Now, of course, any breaking up of a continuous history into discrete eras is a bit of a game of semantics, but these semantic games can sometimes reveal some interesting developments in the history of thought. To my mind, the transition to a distinctly new era of astronomy was marked by the work of two astronomers. And of course, because history in the real world is not a neat narrative, these two figures actually lived some 80 years apart. The first was Galileo Galilei, who took a recently invented device called the telescope and turned it to the heavens. In doing this, he inaugurated what can truly be called the first observational astronomy. Now, earlier astronomers, right down to antiquity, had used instruments to make measurements of the heavens, but these instruments were concerned with finding the position of the sun on the sky or stars on the sky. An important task, to be sure, but one which didn't ever introduce any new questions into astronomy. Galileo's telescope, however, magnified objects and made visible things which had never before been seen. Craters on the moon, rings around Saturn, moons around Jupiter. All these newly observed phenomena cried out for new explanations and radically expanded the scope of astronomy as a science. And so it brought new questions. How much could observations through this device be trusted? Was what you were seeing really out there, or was it just in the telescope somewhere? These were not easy questions to answer, and indeed some of these questions can never be definitively answered once and for all. Some phenomena, like the hills and the valleys on the moon, were real, outside of the telescope. But others, like the sort of rainbow fringes that stars could sometimes take on, were artifacts of the instrument itself. And as long as astronomers use instruments, they will have to grapple with determining what parts of what they are seeing are real and what parts are artifacts of their instruments. As a modern example, even today, not too long ago, there was a group of radio astronomers who thought that they had observed a new kind of transient event, but eventually noticed that it only seemed to occur during lunchtime, and eventually, after a lot of diligent work, traced the signal back to a microwave in the break room. The second radical event in this era was due to the work of Isaac Newton. Newton marks the beginning of what could really be called astrophysics. Now, the distinction between astronomy and astrophysics is a bit academic in nature. The joke in the field is that the difference between astronomy and astrophysics is that if you're sitting next to someone on the plane and they ask what you do, you tell them you're an astronomer if you want to talk to them, and if you don't, you say you're an astrophysicist. A lot of schools have been changing their degrees from astronomy to astrophysics over the past decades for no real reason than that astrophysics just looks a bit more intimidating on someone's resume than astronomy. But modern astronomy is, for all practical purposes, identical with astrophysics. But this was not always so. What made Newton the first astrophysicist was that he was able to show that the exact same laws of physics applied to the heavenly bodies as those on Earth. In the astronomy of antiquity, it was always given that there were one set of laws that determined the motions of the planets in the heavens that the astronomer needed to discover, and a separate, unrelated set of laws that determined the motions of objects on Earth. A central feature of Aristotle's cosmology was the lunary sphere, that is, the sphere corresponding to the moon. In the sublunary realm, the terrestrial realm, one set of physical laws applied, and in the superlunary realm, a separate set of physical laws applied. Newton shattered the lunary sphere and showed that the physics of the terrestrial realm, the motions of grubby everyday objects, applies to the heavens as well. Or, if you want a more optimistic take, the physics of the heavens applies to the grubby objects of Earth and you and I as well. The next roughly 2 centuries after Newton mark a gradual improvement in observational and theoretical astronomy. Astronomers devised larger and more precise telescopes, and the theoretical consequences of Newton's laws get developed. To my mind, the early modern period of astronomy culminates with the discovery of Neptune in 1846. Over the previous 75 years or so, astronomers had been observing the newly discovered planet of Uranus and had been tracking its position on the sky. As a complete orbit of Uranus was traced out over the decades, theorists began to notice that its position did not match the predictions of Newton's laws. By the 1840s, 2 theorists working independently, John Couch Adams in England and Urbain Le Verrier in France, were able to deduce that the anomalies in the orbit of Uranus could be explained if there was another, more distant planet. Using these calculations, Adams and Le Verrier were able to predict the position of this new planet and urged astronomers at observatories to which they had connections to search for this planet. The story here becomes somewhat complicated, but in the end, Le Verrier turned out to be more successful at convincing an observer to look in the right place, and a new planet, Neptune, was discovered within 1 degree of the position that Le Verrier had predicted it. This work was a triumph of both the observational and theoretical techniques of the time. Although Uranus was also discovered by telescope, it actually is barely visible to the naked eye to someone with good eyesight, and in principle could have been discovered without the invention of the telescope. In fact, Uranus had been observed on numerous occasions right down to antiquity, but it had always been mistaken for a stationary star. But Neptune is different. Neptune is too faint to be seen by the naked eye no matter how good your eyes are. It could only have been discovered with a telescope. And the method of its discovery was not serendipitous. In order to find it, theorists had to have developed Newton's laws to such a degree that they could model a planet's motion not only due to the gravitational influence of the Sun, but also including the gravitational influence of Jupiter and Saturn as well, because in fact Jupiter and Saturn both exert a larger gravitational influence on Uranus than does Neptune. This is not a trivial problem. Then, Adams and Le Verrier had to work out the inverse problem of where an 8th planet would have to be if it was going to explain the anomalies in Uranus's orbit. So this discovery required a tremendous refinement in the observational tools introduced by Galileo and the theoretical tools introduced by Newton. The next revolutionary change, to my mind, comes in the mid-19th century, with 2 developments in observational astronomy: the invention of the photographic plate and the spectrograph. Prior to the photographic plate, all astronomy was done by eye. Now, of course, larger telescopes can allow the eye to see fainter objects, but the eye is not a particularly sensitive instrument. It has this issue where it can't collect light for a long period of time, and furthermore, it keeps no record of what it saw. Astronomers would often sketch what they observed, but these sketches were only as good as the astronomer's artistic ability. The photographic plate did two things. First, it allowed astronomers to take real exposures, to make an observation for a long period of time to collect more light and thereby observe fainter objects. And it allowed astronomers to produce a record of what they had observed in a way that could be objectively seen by other astronomers. The spectrograph was equally revolutionary, as physicists began to recognize in the 19th century that different chemical elements produced unique spectroscopic lines. Astronomers realized that this technique could be turned to the heavens to answer the ancient question of what the heavens were made of. The 20th century then saw an explosion in the number of questions asked by astronomy and the methods used to answer those questions. Once astronomers could identify the matter that made up the heavens, they could begin applying the physics developed here on Earth to understand cosmic processes. Until this point, the physics of the heavens was limited simply to understanding the motions of the planets to higher degrees of precision. But armed with the revelations given to them by the photographic plate and the spectrograph, theorists could now study the structure of stars, and from that determine how long stars lived and how they changed over their lifetimes. Careful observation of stars gave astronomers new tools to measure distances to celestial objects. The sheer scale of the universe in space and time started to come into view. Astronomers measured the distances to stars, the size of the galaxy, discovered that there were other galaxies like our own, and then discovered that not only were there a few other galaxies, there were 10 billion galaxies, and that there was more to the universe beyond the limits of what we can see. Fundamental questions like how big is the universe, how old is the universe, finally received convincing answers. And what was most shocking was that the size and age of the universe far exceeded the scope that anyone had anticipated. Astronomers expanded the tools they used to measure the universe beyond the ancient limitations of the visible wavelengths of light to the full electromagnetic spectrum, from radio waves to microwaves, infrared, ultraviolet, and X-rays and beyond. And the scope of observation broke beyond light itself. In the middle of the 20th century, astronomers started measuring particles originating from outer space, cosmic rays. Towards the end of the 20th century, astronomy was being done with ghostly particles called neutrinos, and in the 21st century, gravitational waves, oscillations not of the electromagnetic field like light, but oscillations in the gravitational field, were discovered for the first time. Astronomy in the late 20th and now 21st century has seen the birth of what is called multi-messenger astronomy, where astronomers now can observe events through different techniques simultaneously, seeing an event in X-rays and gravitational waves at the same time, or in ultraviolet light and neutrinos at the same time. In the 1970s, the invention of the charged coupled device, the CCD, the first digital cameras, made astronomers' telescopes 10 times as sensitive overnight, and this increase in sensitivity made possible the later discovery of the first planetary systems outside our solar system towards the close of the century. And yet today, modern astronomy is still occupied with some of the same questions that the ancients were. We have not gotten entirely beyond them. The original problem of timekeeping is today considered more a matter of physics and engineering than astronomy. But planetary motion is not an entirely solved problem. There are still fundamental unanswered questions like, is the solar system stable? More importantly, the question of what the universe is made of is still wide open. Today, the composition of some 95% of the universe is unknown. About 27% of it is something we call dark matter, about which we know very little, and 68% is something we call dark energy, about which we know even less. But let's not get ahead of ourselves. Those were some of the most radical developments in this most ancient science over the course of 3,000 years. We'll have lots of time to dig deep into each of these developments in turn as we progress through the centuries. Next, we will turn to the first recorded astronomy, that of ancient Babylonia, who, over the course of 1,000 years, developed one of the most sophisticated astronomies of the ancient world. Thank you for joining me, and until the next full moon, clear skies.